Alright, welcome to another practice session for algorithm practice and problems. Today we're going to be looking at breadth first search. And in this type of search, we're going to begin talking about more graph algorithms in the following weeks. We did queues last week, so if you don't understand what queues are, you might want to go back and look at that for a bit. Alright, breadth first search. Oh yeah, let me begin first. We're going to practice breadth first search today in different variations. It's a graph traversal algorithm, but oftentimes if you're actually going to do problems and practice them on a platform like LeetCode, you'll also be practicing them on trees as well as grids. And we're mostly going to look at these two forms of problems. There are other formations where you can use breadth first search by transforming the problem into a graph problem, being formally given or being given a set of edges as well. I have an example of being given edges and building a graph, so we'll look at that today, even if there's no explicit graph given in the problem. Some of the, skipped a slide. Some of the non-goals for this problem is I'm not going to formally define graphs, edges, or vertices, or give a formal definition. This is mostly about practice and building that intuition about when to apply breadth first search and how to apply it. We're not going to be looking at like different graph representations and how they're done. You can do it by a matrix. I usually do it with an adjacency list that I build in a hash map. You'll see some of that. I'll go over that in LeetCode 787. And we're also not going to look at problem transformation to graphs. That can be common to do, especially when you do dynamic programming. So just keep that in mind. This is what this little presentation is targeted at. There's also something you can do after you do things in BFS or even DFS. We're not going to look at path reconstruction. Those aren't just happen to not be part of the problems that I've done, but we might look at that in a bit in the future. After you do a graph traversal, it's possible to reconstruct the path where you came from. All right, some of the work that you might want to do before going on with the lecture is trying this problem flood fill. It's a very well-known problem. You've probably used this before if you've ever used Microsoft Paint back in the day. It's just the fill tool where with a set of pixels, you touch one and then all the adjacent neighbors with the same color get turned into another RGB value. That's basically this problem. You can do it with DFS or BFS. We're not going to look through this problem too much today, but hopefully by the end of this lecture, you'll understand how to do this, and this is another great opportunity for you to practice if you haven't done it. All right, so I've mentioned BFS, breadth first search. What is it really? So it's named breadth first search because you search the breadth. You find the nearest unseen nodes so far. This might mean that you use extra memory, or it might not. In this diagram that's provided by Wikimedia, it's on the breadth first search Wikipedia page. You don't really have to track unseen nodes if you're dealing with a tree. What's really a tree? It's basically an acyclic graph. It's a directed acyclic graph. And you can't ever have cycles in a tree, by definition. A graph, on the other hand, you can have cycles. And you will have to keep track of things that you've seen before, or somehow have a way to not accidentally go to a node that you've already been before, at least with the same state. We'll see a problem that's kind of interesting. Using a variation of breadth first search where you might actually visit a C node, but that's part of the problem. Don't worry about that right now, but this is breadth first search. I named it the Imperial Court Advisor's breadth first search because And what we're going to be talking about today, this is really about expanding territory. And that's how I understand breadth first search. It is an expansion rather than in depth first search, where you kind of just go as deep as you can and then backtrack. This is a different algorithm. When you look at the order of the expansion, and in this diagram we have a tree, first you have the root node, let's say we start at F, and then you're going to expand, right? What are the nearest nodes to F? Well, you're going to have B, and you're also going to have G, right? Those are the nearest neighbors. In a depth first search, which we haven't talked about yet, you're actually just going to repeatedly choose one of the neighbors and then backtrack when you've gotten deep enough, right? So F would go to G, and then G would go to I, and then H would find node children to go to, and then we'd backtrack all the way up the chain, and then after that we'd go and find B, perhaps. There's different flavors of depth first search: pre-order, post-order, and in order. And there's different flavors of even those, but we're not going to talk about those because today we're just talking about breadth first search. And just remember, it is really about expanding a frontier. But once you have B and G, where do you expand to next? Well, you have to expand to the nearest unseen nodes. So the nearest unseen nodes are A, D, as well as I, right? And you can see that when you enqueue these things to see next, you're really using a queue data structure, right? So F can put into, so we can start off, right, with F as our queue. And then the next, okay, so then our queue starts off at F, right? And then we look at F, right? And then we enqueue two nodes. So what does our queue look like? It looks like B and G. And then our next state of our queue is actually we're going to pop off B and we're going to add in A and D, right? This is some kind of intermediate state for this level. And then we pop off G, right? And then A and D are in front, and then we put in G's children, and then you have I, right? So this is, after traversing this level, this is the state of our queue. All right, but then what comes next? Well, what happens when we pop off A?
No children.
No children, right? So this is the intermediate state of the queue. You just only have D and I in the queue. And then we pop off D, right? So we have I in the queue now. But now we look at the children, we see that there's C and there's also E. Right? And then we pop off I, you have C and E in the queue, C and E in the queue, and I has one child, H, and you can see that as we move forward, you're just going to have E and H, and C has no children, and then you just have H when you pop off E, and then finally you have nothing. So from start to termination, this is what the state of the queue would look like, right? You expand things. Okay, so that is it. That's basically BFS. It's got some pretty, it's pretty simple to implement, and the time complexity is linear, right? It's linear, and how do you reason about that? Well, if you looked at breadth first search, at least for that tree example, right? You visit a vertex once for every vertex, right? So this is, if you were doing this calculation about counting, the constant multiplier would just be 1, right? Times the amount of vertices. Assuming it's all connected, right? Assuming it's all connected. And for the amount of edges, really for that tree, it's looked at only one time, right? Because for each node that you're at, you look at that edge only once, right? There's no, when you're at G, you don't go back to look at F since it's a tree. If, however, this were a bidirectional graph, you would be carrying around maybe some set called scene, right? Which would be of, in Python, this is how you make a set. But G would look back at F, right? Maybe look at that edge again, but see that the element is in scene. So in graphs, actually, this constant is actually 2, right? Times the number of edges, which is still constant, right? So this is going to be just the number of vertices plus the number of edges, time complexity, even when you're dealing with a graph, right? This is simple and easy to write iteratively rather than recursively. And we'll see the pattern. It's very straightforward, but it can take a little bit of time getting used to. I think I could have done, well, anyway, I'll talk about that when I get there. Okay, but what are some of the disadvantages of breadth-first search? It consumes more memory than DFS in some cases. It's because DFS takes one direction at a time. The stack might go very deep, but BFS can do things in parallel. And this means that if for each node there are many children, this can get really explosive really quickly on the amount of memory that you need, right? So if each node has a branching factor of b, right, there's many edges. And if you go deep enough, right, and if every single child has that amount of outgoing edges, then very quickly you're going to have a lot of nodes in memory. So that can be one disadvantage. So if you're dealing with a graph that has a ton of edges, it's very, very dense, then you might consider not using a basic DFS. There's other algorithms such as A*, or even Dijkstra would be faster in this case. When edges have weights, you should generally maybe not think to look at just a plain BFS. You probably want to consider Dijkstra's if you can. There's other algorithms as well, like Floyd-Warshall and Bellman-Ford. We're not really going to talk about those, especially not in this lecture. Oh, and I guess I should say what are weights. Basically, in a graph, you can think about this as like, cities, right? Cities have a cost, right? Between either, maybe you're building a road and this road might cost $5 million in order to build, right? And from city B to city, let's say C, there's another cost to that edge, right? It can maybe cost $6 million. But there's an alternate plan that proposes maybe a different route, maybe from C to B. Maybe this one's light rail. Maybe this one costs $8 million, right? So in a graph, you can have costs associated with edges, and this can change what kind of graph traversal algorithms that you use, because you might have different goals when you do that graph traversal. Mainly when you think about BFS, you're thinking about single source shortest path, meaning that you are starting at a particular node and you want to find what is the cheapest or what is the quickest or what is the fastest way to get from a particular node to a destination. There's other algorithms that compute the shortest path from every node to every other node. You can look into Floyd-Warshall if you're interested in that, but we're not going to talk about that today. We're just mainly going to try and practice breadth-first search, but just know when to not try and use breadth-first search, and when to use perhaps other algorithms that we'll talk about later. I'm going to do a brief comparison to depth first search right now, even though we haven't covered it. Both are viable for traversing a graph to identify nodes, and also to identify path costs, but in BFS, the path costs have to be uniform. For basic BFS at least. Because breadth first search can handle, hey, how many hops does it take to get from node A all the way to node Z, right? Because when you expand, there's an implicit cost of, let's say, hey, that's one hop, that's another hop, right? So breadth first search is classically really good at traversing a graph to identify path costs when the path costs are uniform. Depth first search can do a little bit more, but it's not efficient because depth first search cannot know when it has found the cheapest cost without traversing absolutely almost every other possibility. So in that case, breadth first search wins. But just know that they're both viable. It's just that breadth first search is going to be faster in that case, or preferable because of its characteristics. In both of them, when you are looking to go to a particular depth, breadth first search, it's really straightforward, but in depth first search, it's also pretty straightforward, right, when you have a depth bound. It's harder to write an infinite loop in BFS, and especially when you write depth first search, as I do, I tend to write DFS recursively, and sometimes I don't catch my base conditions, and I'll have an infinite loop and then have to debug why. So in breadth first search, that's kind of harder to mess up, and it's easier to debug because you can just print out the queue every single generation, right? Fairly simple to do, so I find it easier to debug as well. Both will still require you to keep track of which nodes you've seen when you deal with a graph in cycles. And treat BFS like a parallel search, and depth first search is more of a backtracking type of search. I say this because really you're dealing with expanding, and when you expand, these might find different nodes, right? Or they might actually end up finding one of the same nodes, right? When you're dealing with a graph, you can actually find a node that has maybe been enqueued by another child that you had in your current generation. So it's important to screen out things with, maybe a set, or depending on the problem, a dictionary that holds some other data. So that is my brief comparison. You'll see me compare this again more in detail when I eventually go through depth first search. But that's the gist for now. Oh, and one more thing is BFS tends to use a queue, and depth first search tends to use a data structure, a stack, and it's still a stack if you use recursion. It's just that there's an implicit stack for the function calls. We'll talk more about that later, or you'll probably see this more formally defined or explained when you take a formal algorithms class. So let's look at some applications. Honestly, I feel like a lot of these applications are pretty easy to come up with because it's a foundational algorithm, and because it's one of the algorithms that's used to come up with even better ideas about finding the single source shortest path in a network. So note that many of these applications can also be done doing DFS, and have in the back of your mind when you can use DFS or BFS. There's actually a lot of problems. Even if they're only marked with depth first search, you can probably use breadth first search as well for the problem, where there's problems that are marked breadth first search, tagged breadth first search in LeetCode, that you can actually just solve using DFS. So keep in mind when you would prefer one or the other. You'll generally find yourself preferring one style of implementation over another. So yeah, just have in the back of your mind when you would use one for the other. So one way you could use this is for an application like Google Maps or Uber, right? Breadth first search performs to a source to all the points of shortest paths. So we said SSSP, single source shortest path. You can find the shortest path, right, to a set of nodes if you would like to, right? Let's say this is node X and this is node Y. You can actually find, when you do a BFS from point A, the shortest path to X is 2, right? Because you'll see that in 2 generations later. And the shortest path to Y is also 2 because it's 2 generations later. For more complicated graphs, you might see something like this, right? In which case you'd see Y, at generation 1, basically, right? Because this is only one hop, right? You don't have to go through these 3 hops. And basically when you've seen all the vertices, whether you keep a count and a set of all the nodes you've seen, and if you've seen all the nodes, you can exit your breadth first search, right? And then in a table, you would know the minimum cost to each node, right? You can use algorithms like this, but technically Google Maps and Uber are going to prefer something more efficient. Dijkstra is a possibility, but I highly suspect that A-star search algorithm is actually used, but we're not going to be talking about A-star today. I haven't looked into A-star very much, but from my brief glance, you probably want to understand Dijkstra before you understand A-star. I'm not going to talk too much about A-star either, but it's a very powerful algorithm that I suspect is actually used more in real life than just generic BFS for this type of application. Dijkstra itself can be thought of as a variation of BFS, and it's going to be faster for a lot of cases. Dijkstra uses something called a priority queue instead of just the normal queue, and it's how it gains a lot of its properties in its search algorithm. But yeah, this is briefly one application you could use. Just be careful to note, because of how BFS performs, you probably care about doing this for smaller data sets rather than super large data sets. And if you're interested in how Google Maps or Uber works, they actually have papers that are published online. And I believe, at least for Google Maps, you actually download these things called map tiles. So they actually do a lot of graph compression, where you might have too many nodes in a particular section of the Earth, right? But it's possible to compress it into, maybe let's just say represent it as a single tile. And a single tile would be a single node, and these tiles themselves would form a graph, right? And you can kind of get a rough distance, maybe that's not perfect, between going from tile to another tile, and use a graph traversal algorithm over that. And then when you know the tiles that you need, you can then just isolate the graph into just the nodes inside those 2 tiles, instead of expanding. If you're trying to go to Las Vegas, you don't have to see what's happening in Chicago, right? So there's ways to make an efficient graph, as well as making the algorithm itself more efficient. But we're also not going to talk about that, but that's just a little thing if you're curious. Another application is probably something I just talked about. You can identify all nodes in a graph, right? You can identify, whether you're dealing with a network, you're dealing with maybe a server, and you want to see all the other servers that it's connected to. You could do something like a breadth first search to list out, what type of hardware you have listed. Maybe you're dealing with printers and stuff like that. But that works only as long as there's edges to nodes. When you're dealing with a real network, sometimes those edges, right, you can't reach a node, and you're not sure whether there's just no path to it or whether the network's just flaky. DFS can also be used for this use case. We all use social networks these days to some extent, right? When you use LinkedIn or Facebook, you get recommended friends, right? You're generally going to be recommended the people that you share something in common with. And in Facebook, they actually model all their entities as, well, basically graphs. Facebook actually uses a graph database for the things that they do. So if you are some friend, right, you're person A, and you want to be recommended your friend's friends, well, your friends are this person right here and this person right here. You might actually know these people that are circled in yellow, right? Or you want to find out a way to get connected with someone. What degree of distance do you have from someone? Who can introduce you? This might also be another application that you can do using BFS. You can use DFS technically here, but I find breadth first search is much more conceptually natural in order to do this. This actually has to deal with more of A-star, but I feel like A-star is also still just a variation of breadth first search, so I included this slide, but you can feel free to heckle me if you disagree. So I'll just read this quote. This is from the Godot docs. Godot is a game engine. This A-star 3D class is an implementation of the A-star for finding the shortest path between two vertices on a connected graph in 3D space. Why would you need to do this in game engines? Well, it's because you generally, in a lot of games, especially RPG types, that have, that's not turn-based, that's, real-time, you'll have enemies that need to path to your character, or you'll be controlling something that you need to path from one location to another. And you probably don't want, if you're moving some units along, some group of people along, and you want to move them in order to get to this castle place, you probably don't want them to take a path like this and end up at the castle when you can just go straight here. So this is such a problem in video games that instead of reinventing the wheel, there's just a class that you can plug in into the game engine's implementation of A-star 3D. So yeah, that's that. This also works when you're dealing in computer vision as well. A-star is used like a lot. The variation of BFS is that instead of like traversing like all possible edges, you might in A-star only traverse the exact path that you need. And you do that by combining kind of like a priority queue with also a heuristic on which edge is maybe good to go towards. And combining those two things, roughly to my understanding, because I haven't formally studied A-star, is how you arrive at A-star. So it is still just a variation of BFS, in my opinion, but let's not worry about that. I think I'm spending way too much time on this. The last thing is flood fill. This is a brush tool you've probably used before. This is a cool GIF I found online on Wikimedia about how to expand. It's just a visualization about how flood fill is actually working in slow motion. You can, of course, use DFS for this use case as well. I'm going to talk about one essential problem now, and then I'm going to show you the pattern, and then I guess we can take a break, and then I'll come back and show you these two other problems. The problem I'm going to show you is maximum level sum of a binary tree. I'm going to talk about the pattern, things you'll get wrong, and things that you can hopefully get right. And then I'll talk about, I definitely want to go through rotting oranges, and I definitely want to go through cheapest flights within k-stops. This is where I'll go through an algorithm that is called SPFA, in which you can deal with a weighted graph using a variation of BFS. This is also a variation of the Bellman-Ford algorithm, if you know that one. If we have time, if I feel like we have time, we should do minimum score of path between cities. So that's the plan. I feel like I'm 40 minutes in now. I might actually only be 30 minutes in. But first, let's look at this problem. And this is really a problem that you can use actually as a template for many other problems. And in the back of your mind, think about whether you can use DFS for this problem. Whoops. Well, I'll give you a minute to read the problem, and then formulate what you think you might be able to explain. And then, then we'll discuss about it. So I'm going to set the timer for a minute starting now. And I'll give you a chance to read through the problem.
This one has a pretty short explanation, so I think I see it.
Okay, great. Cool, yeah, we can discuss now.
Okay, would you rather leave more time in the recording or anything?
Nah, in the recording, people can just pause.
That's true. So the benefit of breadth first seems kind of obvious because we're asking about each level, right? We're looking across, right? Not up and down, so to speak.
Right, breadth first search naturally has this iteration order where we're gonna look at that, where we expand by level already. Yep.
Thinking about depth first search, I think it's conceivable that you could get there, but you would need some way of tracking what level any given value corresponds to when you encounter it, and then backtracking to other branches and checking for corresponding level values at the corresponding level that you already computed, and find a sum and do comparisons that way. I think it's possible, but probably less clear. But I'm not sure.
Yeah, no, I think you said it right. If you do a DFS, what you can do is you can keep track of, level sums, right, in a particular, let's say, array, right? And as you go through the DFS, what you can do is a pre-order traversal. So you would do something like level sum, and then for that particular depth, you would plus equals no dot value, right? And then you could do DFS, and then do no dot left, and then no dot right. And that's basically the skeleton for how I would solve that using DFS. So you could do it that way, right? You'd keep a separate maybe array, and then you'd have to loop through over the array when you're done, or keep track of the max that you've seen somehow. But yeah, totally doable with DFS. I find that BFS is more natural for this problem. And let's look at how to do that in BFS today.
So, I feel like I almost see it, but the question becomes I think you could have, for example, a node with only one child, right?
Mm-hmm.
I know it's at most two.
So the level starts at 1. That's all it's saying. The level of its children is 2. Yeah.
But it's a binary tree, so the number of children is at most 2.
Oh, yes, yes, yes. It's a binary tree. Yeah,
Can it
correct.
can it be just 1, left or right?
Yes. I believe you can have nodes that are only going to have one child. Yes, that's possible.
Right. Because so I was trying to think about how I do it, and it's if you have my overall question is, how do you know what level you're on just by the state of the queue that you have? That's where I think I'm stuck. But otherwise, it's pretty clear that you would in queue. So in example 1, you would in queue 1, that would be the sum corresponding to level 1. You DQ and then NQ its children, and you could look at the values of the nodes in the queue, and that corresponds, and sum those, and that corresponds to level 2, and compare. Right? Is
Yeah.
this making sense?
Yeah, that makes sense. So BFS, you can write it in different ways. So after 1, right, the state of the queue is just 1 when you start off. You pop it off, and you'll have 7 and 0, right, as our nodes. What you can do is, basically the trick to this problem is like figuring out which level. Just making sure that the sum corresponds to that level. If you didn't really care about like grouping things in levels, right, you could just like not worry about, well, this extra thing that you have to keep track of, right? Because in breadth first search, naturally, like you don't necessarily, you just deal with expanding, right? It doesn't explicitly have this concept of a level on its own. So I'm gonna start writing some code. What you can do is basically, hey, when you can have basically, you can record the length. I can record, hey, this is length 2. I'm only going to iterate 2 nodes, and that's going to be the sum for this level, right? When you start dequeuing things again. So it might be better if I just show you your idea, essentially. I feel like my computer might be a bit slow or something. Let me check how my RAM's doing. Or not my RAM, my CPU. So I feel like LeetCode is really lagging.
Before it said it sent me to like Cloudflare error page, and when it was really slow to load, it said it was a server side problem. So I don't know how accurate that is, but
Oh, maybe
I think
LeetCode's
on the
having...
weekends they're just impacted.
Well, it's working right now, so I'm gonna go for it. So we start off with a queue, right? And we know something about where we should start. Where we want to start is actually the root node. It's pretty straightforward because it's a tree, but for some problems, they will specify differently. So I'm gonna use this as my break condition, right? While queue means basically go until the queue is empty, right? Because in Python, this is a falsy statement, I believe. But you can just write while queue. And what am I going to do? I'm going to actually record what the queue length is. So this is the length of the queue. And then I'm going to do it queue length times now. And the way I'm going to do that in Python is for underscore, in range of queue length, I'm going to do node equals queue dot top left, right? So now I have access to the current node. I'm going to want to keep track of now two things, now that I realize it. I'm going to want to keep track of the max level sum, right? I think, unless we have negative values, we do have negative values. So the deepest negative value is negative 10 to the 5th, and the number of nodes is 10 to the 4th. And these values will fit inside a 32-bit integer if you're doing this problem in C++ where you have to care about integer types. I'm just going to use math.infinity kind of like as a sentinel kind of value. And I know that every level is going to have a sum, and I'm going to start that off at 0. So as I pop things off, I'm going to update the level sum, and I'm going to update that by adding the node's value to it. At the end of the for loop, I am going to update max level sum. But I also have to keep in mind the problem. I only care about the smallest level x, such that the sum of all the values of the nodes is at its maximal. So I'm going to say that this is the result. That level is, I'm going to start it off at -1 because I know that's just not a right level. And during the iteration, it'll for sure update if we code things correctly. So if level sum happens to be less than, or no, happens to be greater than max level sum, I'm going to update two things. Result equals, I guess I can keep track of the current level. And also max level sum is now equal to the level sum. I need to make sure that the level increments each time now as I do this BFS. And what I did not do here that I left out is I need to now enqueue things onto the queue. So queue.append node.left, and I need to remember to screen it out because if it's null, that's not going to be something I want to get an error for when I access the node.val on the next line. When the queue, recycles and like I get that element, right? So you really want to prevent nulls from showing up. So only if it's truthy am I going to enqueue that. Same thing with node right. And at the end, we want to return the result. And I think that's the general gist of it. So I'm just going to run that, and it might fail. Oh no, it actually passed. Okay, so I guess I had no syntax errors. That's basically breadth first search. You can record the length of the queue, and then just for all the elements in the existing queue, just pop them off and get the sum for that particular level. Do your same thing, and then once you're done with all of the children in that level, then you can do that comparison, right, and increment the level. It is also possible. Did you go ahead?
So I'm not sure I see how it handles the issue that I was first stuck on, and I believe it does. I just am not seeing it. Is the state of the queue always such that everything on the queue is at the same level?
So that the answer to that is no.
Right.
So let me clarify this. I think an example might be good to see. Let's start at level 2 right here. I think we can agree that like level 1, leads to this state of the queue, right? So what happens is that so queue length right now is 2, right? So I recorded this, so this is a static value now, right? This is 2 for this entire piece of code, right? For this iteration. Queue length is going to be 2, meaning that when we do like queue.append, this stays 2, right? No matter how many nodes we pop off and put on, this is going to remain 2 for this entire iteration of this while loop right now. Because we have 2 elements, what's going to happen is, okay, so level sum, right, starts off at 0, but once we pop the 7, right, we do 7 plus 0, right, so now level sum equals 7, and the state of the queue is such that we have node 0, right, because we haven't popped that off, and then we have this other 7, and because this is, this is truthy, we're in line 21 right now, we're going to put that on the queue, right, and then we go to this node, right, because that's this line 22, we put on -8. So this is the state of the queue after we pop off that 7, right? This underscore, I don't use it, but if you were to print it out, this would go from the value of 0 to the value of 1, and 2, it would basically break out of the loop. So this first element is now seen, right? So this would happen during iteration 0 in this for loop, right? So we put on these 2 new elements, right? These 2 new elements, I'm going to claim we're not even going to look at inside this for loop, right? These are omitted from this for loop. They're not going to be looked at all. So this 0 comes now, right? We're now at iteration 1, right, in this for loop. And this 0 actually has no children when we pop it off. So the queue actually doesn't mutate, but we do have the chance to do line 20, but 7 plus 0 is also just 7, right? And then, because the original length of the queue that we recorded is just 2, well, we saw 2 elements, so we break out of this for loop now. So we're done with the for loop, and we're at line 24. So if that doesn't make things clear enough, I'm actually going to print the iteration that we're at, and I'm also going to print out the node's value. And I'm going to print a statement that says new level traversal, so we know it's being traversed at each level. So we have a new level traversal when we look at the value of 1, and we're only going to, and this is the first iteration of the for loop, right? First iteration of the for loop, we see 1, and that basically is the end of the level traversal. In the next level, right, on iteration 1, we see 7, and the next iteration, we see the value 0. And we stop, quite notably, even though that 7 and -8 were in queued, because of how we structured this for loop. And the next level is 7 and 8, and there's no other children. So that's that level traversal. I think they included a more, yeah, included a different example here. But does that make sense so far, or should I talk about that a bit more?
The example absolutely makes sense. it's the specific. I think for me, it's seeing through to the specific generalization that guarantees that everything we're summing together corresponds to one level. And the way we're doing that is by taking the length of the queue at each point in the outer loop.
Mm-hmm.
And by only popping len number of times, or yeah, we're guaranteeing that at the next step of the outer loop, everything that's left on the queue corresponds to the next level. Is that right?
Yeah, that's essentially it. One way to also write this, if you like writing it that way, is you don't actually have to use this type of construction. You can actually create another queue if you want, and basically if you wanted that separation and use the data, use basically a separate queue and then just like garbage collect your existing queues, you could do something like this if you like. And this would also work. So what I did was, I'm going to say that for next level, I'm going to use a new queue for that, right? And so for the existing queue, I'm going to like, oh wait, no, this doesn't work that way. Sorry. Yeah, you'd still want to use some kind of construction for a for loop. You'd say while queue, I guess. You can have this nested thing. And then you wouldn't have to care about queue length at all. But you could create a new queue that essentially is the queue that you append to from what is existing in the current queue. And then you would set the reference for this variable queue to that next queue. So this is also another way to do it if you don't want to keep them all conflated in the same queue. All right, does that make enough sense? I can go over it a bit more or clarify other details.
The general idea makes sense to me. I think maybe the issue of tracking levels is one of those things that once you see it is so obvious that it's to see. But if we go through more, we don't have to harp on it. We can go through more problems.
Sure. Yeah. This is just the general pattern I do for the level. If you did not care about which level it was, you would not need an inner loop, right?
Mm-hmm.
If there was a problem, like you did not care about the levels at all, you could use this type of construction, right? Where it's just inside the queue, you pop something, and then you check whether it's valid to add that thing, and then you add it, and then just allow and don't worry about the levels, right? This is how you would maybe write something like that, the general structure.
Right. If we're looking for like the largest value in the tree overall and needed to do it breadth first.
Right, if you were doing things by just node instead of level, right? So, let's see, my computer feels like a bit slow. All right, how do you recognize that a problem is asking you to do BFS, or that BFS is just a good way to look at the problem? you might see some hints in the problem description itself. Someone says, hey, you need to find the shortest path from one node to another. Generally, you just want to think about BFS and other algorithms like BFS, and don't think about DFS as much. This could be like the minimum cost or the minimum steps, the least amount of time. Usually, generally, if this is not for something that's weighted, also keep in mind that you don't need the shortest path from all nodes to all other nodes. If you were to do that in BFS, you would run BFS for each individual node. And you might consider, instead of using something like Floyd-Warshall, just keep in mind that Floyd-Warshall, I believe, is cubic time. So yeah, just shortest path from all nodes to all nodes is generally not going to be very fast. You also care about doing BFS. I just mentioned this. When edge weights are uniform, if it's much simpler to implement, use a BFS for that. When edge weights aren't uniform, you can still use BFS using the SPFA. It's called shortest path faster algorithm. It's either a variation of Bellman-Ford, or it's also called Bellman-Ford sometimes. But it's slower than Dijkstra in general. But it can handle negative edge weights. Dijkstra can't handle that. So we're actually going to see an implementation of that in cheapest flights within K-stops. I find that to be like a really interesting and useful problem to do, especially if you're dealing with graph algorithms. I would not skip this problem. All right, so the essential pattern of a BFS solution is you'll generally try and initialize variables, and often you care about how many steps happen from a source node, because that's basically going to be your cost. So you might initialize the step as 0, or maybe the step as 1, or if there's some arithmetic for you to do. In Python, we use the deck as the queue, and you might fill in the queue with some elements. You'll have to decide on which elements to start with. In a graph in general, but you don't have to worry about this if you're dealing with a tree, you're probably going to create some kind of set, or maybe some kind of table, to know whether you've seen that node before, so you don't accidentally enqueue something onto your queue that you've already seen before. When you start the BFS, you can basically always start with this line. As we saw before, you can get the length of the level, and this just tells you, okay, in this inner loop where I'm going to process each of the nodes, I'm only going to process maybe 4 of those nodes, because I know that only 4 of them belong to the current level. So you end up popping, doing only, maybe in this example, 4 pops, right? And for each of those nodes, you have to find what the neighbors are, right? Maybe this isn't a binary tree, maybe this is an n-ary tree, maybe this is some kind of graph where you care about like the levels during a graph traversal, right? You could use something like this. So the node.neighbors, like this is just pseudocode. A lot of times you'll have a graph data structure and you'll find the associated neighbors from that graph. You'll generally screen things out, like maybe the next node isn't valid. Maybe you're dealing with a grid and the calculation that you do for the next node actually brings it off the grid, and in that case that node's not valid, right? If the node you've seen before, you also don't want to process it, and it's only if it passes these 2 checks that you'll do some processing for it. You'll say that, hey, you've kind of seen this node, there's no need for some other node to enqueue it onto the queue, and you also then enqueue it. And this is a mistake. This step line should not be here. It should be out here at this indentation level. You'll want to increment your step after you're done processing the entire level. Of course, if you don't care about the level, don't worry about this outer for loop. You're allowed to just do all the stuff inside the current for loop. So treat this as optional when you don't care about the length. When you don't care about the level that you're at. or whether your traversal inherently doesn't go by the level, as what happens when you deal with something called, as what happens when you use Dijkstra's algorithm, right? So this is just for plain BFS when you care about the level. All right, so that's the general pattern. You can kind of use this template and it shows up in basically every time you use BFS. So that's the general pattern, but of course, how do you fill in those details? Those are the things you want to get right. You want to understand what does each node in the BFS represent. You'll see that sometimes when you use BFS, we'll actually associate some metadata with each node as well. That's one possible way to use BFS. I've actually shown that on the previous lecture, they're in previous lecture slides where I did a problem using BFS, but I didn't go over it during the actual lecture. The node could be something like a node in a graph, could be a cell in a grid, could be a state in a dynamic programming problem. But don't worry about that last point. We're not going to talk about dynamic programming problem until probably a few weeks from now. Sometimes we store cost to accumulate so far how long with a little node itself. So in addition, if it was a node in like a graph or a tree, you might store the cost accumulated so far to get to that particular node. All right. You could have actually used this strategy in the previous problem that we saw by just saying, hey, I'm not only going to enqueue the node, I'm going to associate, hey, this is actually going to be associated with level +1, right? And if you associate each node with a piece of metadata, and this metadata being the level, you can actually accumulate the level sum by accessing the second element of that level and then just incrementing the level in the correct place. So that's one possibility of doing that. It starts looking a bit more like DFS when you do something like that. But I don't think I have too many examples of doing that right now, but it's definitely a way to use BFS that we might do definitely in a second lecture on BFS if we get there. All right, so you want to get rid of what does each node in a BFS represent. You also want to know what the starting elements for the queue are. Sometimes in a graph, you might decide that you can start at multiple nodes. We're actually going to see an example of this in the very next problem after the break. And you also need to care about what the conditions are for pruning a child or neighboring node. It might be a visited set, it might be a cost table visiting that node. Actually, I take that back. We actually do have an example of storing the cost accumulated so far in 787. And we're definitely going to go over that. One thing I do want to just go over it a bit is that in the previous slide, there is a reason that I do the pruning in the parent node, right? The parent node is visiting the children node. It's very important to do pruning at this stage, because if you did pruning when you were dequeuing the element, it's possible to enqueue a lot of duplicates, right? So maybe you have a graph where you can just, if you did not have this check here, you would just enqueue into your queue a whole bunch of duplicates. You could deduplicate that by, if next node is in the scene now, continue, right? Don't process it. But you could potentially have an exponential explosion of memory if you don't prune at the parent. I'll actually show you some examples of where I mess up and actually have a time limit exceeded because I did not prune at the parent node. So I'm not sure if textbooks really talk about this, but it was definitely not covered when I was learning BFS for the first time. You definitely want to prune while you're at the parent node when you enqueue children if you can. anyway, onwards. I think that is actually the last thing that I said. And almost always you can prune children while at the parent node. This is for basic BFS. In Dijkstra, it's only slightly more complicated than that. We're going to talk about some problems now, but we're going to take a break. Let's take a 10-minute break starting now and come back, think about some questions you might have. If you want, read through this problem of rotting oranges, but otherwise I'll read it out when we get back. And we'll see an interesting application of BFS for this problem. All right, sound good? Or any questions?
No, sounds good. See you in 10.
See you in 10.